Dear students, welcome back after the break. So, before the break we are talking about usage of current mirror for CE amplifier and also CS amplifier. Now, we also can see that usage of current mirror for common collector amplifier as well. So, here we do have the transistor level circuit. Transistor 1, it is the main amplifying transistor, input port is here and then the output port it is here. And earlier what we said is that the current of this transistor it can be set by one reference current. So, instead of having reference current, this is what we do have the implementation of the current source. In fact, if you see that it consists of a bias resistor RB, maybe you can say BIAS bias. So, VCC to collector of transistor 3 we do have this R bias, and based on the value of this R bias we can get a current here, and we may call this is I ref, the reference current, and expression of I reference equals to VCC minus VBE on of transistor 3 divided by R bias. So, that is the reference current, and we do have the current mirror getting constructed by transistor 3 and transistor 2. And if we ignore the current the early voltage effect and the beta loss, so we can say that the collector current of transistor 2 IC2 it is well approximated by Is of transistor 2 divided by Is of transistor 3 multiplied by IC 3. So, this is the exact equation assuming transistor 2 and transistor 3 they are identical, and then this may be well approximated by Is 2 by Is 3 into this I reference. And strictly speaking, this approximation it is associated with the drop of the two non-ideal factors, namely 1 plus difference of the VCE voltage of transistor 2 minus transistor 3 divided by early voltage, and in the denominator we do have non-ideality factor which is 1 plus. So, it is in fact it is function of beta and all. So, we do have 1 by beta of transistor 3, then 1 by beta of transistor 2 multiplied by whatever Is 2 divided by Is 1 sorry Is 3 and so on and so. So, here we assume that this non-ideality factor it is approximately equal to 1, and hence we can approximate this collector current equals to this reference current multiplied by the reverse saturation currents ratio of the transistor 2 and transistor 3, and the I reference current is given. So, that sets the emitter current of transistor 1. So, IE 1 it is equal to IC 2. Now, once we get the DC operating point, then to find the gain from input to primary output, we can draw the small signal equivalent circuit. And since the current mirror here it is not carrying any signal, so the equivalent circuit, small signal equivalent circuit coming out of the current mirror, it is only RO of transistor 2. So, that is what we do have here. This is the model of transistor 1, and collector is connected to VCC, which is AC ground, and at the emitter we do have RO2, and rest of the things in terms of signal, it is not carrying any signal. So, that can be dropped. And again you can analyze this circuit to find what will be the corresponding gain. So, AV equals to, which is defined as VO divided by V in, and that we have discussed that its gain it is GM 1 plus 1 by R pi, and then divided by GM 1 plus 1 by R pi of transistor 1 plus 1 by R O 1 plus 1 by R O 2. Okay. So, similar to common collector amplifier, the current mirror can also be used for common drain amplifier, which is the MOSFET counterpart of this circuit. So, in the next slide we will see the circuit here. Here we do have the main circuit. Transistor 1, it is M1, it is primarily the main circuit, the amplifier circuit, which is connected in common drain configuration. This is the input port and this is the output port, and here we do have the bias circuit. We do have say resistor R bias, and this R bias it is connected between the supply voltage and the diode connected transistor M3. So, we can say that VDD equals to I into whatever I bias we do have, or we can say I reference multiplied by R bias plus VGS of transistor 3. And on the other hand, on this reference current I ref is also equal to VDS 3, which is of course K multiplied by W by L of transistor 3 by 2 into VGS 3 minus VT squared. So, we may drop the 1 plus lambda VDS part, and so equating say or utilizing say these two equations, we can get the I reference current, and that reference current I reference that defines the IDS current of transistor 2. So, IDS 2. So, IDS 2 it is equals to in fact it is function of W by L of transistor 2 divided by W by L of transistor 3 multiplied by this I reference current. In fact, this strictly speaking it should be multiplied by 1 plus lambda into VDS difference, VDS difference of transistor 2 minus transistor 3. So, so this part of course, this is VDS of transistor 2 minus VDS of transistor 3. So, by dropping this part or approximately making this part equal to 1. So, we can get the expression of the current here, which defines the current of transistor 1. Again by once you get the DC operating point, then to get the input to output relationship, you can draw the small signal equivalent circuit. Similar to the previous circuit here, since the current mirror is not carrying any signal current. So, it is small signal equivalent circuit. Out of the current mirror, it is only the RDS of transistor 2. We are denoting this by RO2, and then by analyzing this circuit, we can get the voltage gain equals to, which is defined as VO divided by V in. So, that is equal to GM divided by GM1 divided by GM1 plus 1 by RO1 plus 1 by RO2. This we already have derived before. So, that is how we can find the gain, and that is how we can get the corresponding operating point for the common drain amplifier. Now, of course, since both the resistors are very high, you can well approximate this by 1. Now, next thing is that the current mirror can also be used, or rather frequently used for differential amplifier. So, our next topic or next subtopic it is how current mirror can be used for differential amplifier. So, in fact, there are different possible applications, and the applications of the current mirror on differential amplifier, it is having 3 folds. One is for replacing this tail resistor, and if you replace this tail resistor, that will improve the common mode gain, and then you can replace these 2 loads by active load, and the active load can be biased using current mirror. And then in addition to that, instead of having the active load biased from external current reference or DC current reference, we may replace this by something called current mirror load. So, this current flowing through this left half can be mirrored into the right half, and that mirroring it is different from normal DC mirror, because this left arm it also carries some signal, and once you make the current mirror here, obviously the signal also propagates from left to right through that current mirror, and its consequence it is that it improves both the differential mode gain as well as the common mode gain, which means that the active current mirror load, it improves the differential mode gain and decreases the common mode gain. So, let us see one by one how the replacement or utilization of current mirror can be deployed to improve the performance of differential amplifier. So, in this circuit what we mentioned here, it is essentially this RT we are replacing by a current mirror here, and this current mirror, it is of course, its current it is set by the DC supply voltage and then R bias and whatever its dimension we do have. In fact, similar to the previous case, here again if I say that this is the reference current I R E F reference, then you can say VDD equals to I reference multiplied by R bias plus VGS of transistor 4. On the other hand, I reference, so I reference it is also equal to IDS of transistor 4, and we know this IDS and VGS, it is having known relationship. So, K W by L by 2 into VGS 4 minus VTH square. We can drop the 1 plus lambda VDS part, and again utilizing these two equations we can find the reference current as we have discussed earlier. So, once you get this reference current, from that you can find what will be the corresponding current flowing through transistor 3. So, in fact, that gives us IDS 3 or tail transistor current. It is primarily defined by this I reference current multiplied by W by L of transistor 3 divided by W by L of transistor 4 because of the current mirror property, and then we can also consider 1 plus lambda VDS, or probably you can drop this part lambda VDS 3 minus VDS 4. So, assuming VTH of these two transistors they are equal and their corresponding K parameter equal, and assuming lambda of the two transistors are also equal, we do obtain this current equation. And note that incident this ratio it is also there. In case if this ratio aspect ratio of transistor 3 and transistor 4 are same, then again this part it will be 1, and then this current it will be I ref. Otherwise, if this ratio it is having some other value, then we can get this value different from I ref, but nevertheless this I reference current it is defining the tail transistor current. Now, in contrast to this circuit which you have discussed before, if you change the DC voltage or common mode DC voltage in the circuit coming here and here, if you vary this DC current, this node voltage, the source node voltage also changes. And if we have a simple tail resistor, if this voltage it is changing, then the corresponding tail current also changes, and the corresponding DC voltage as a result at the output DC voltage that also changes. Now, in comparison with this, if you consider this circuit having the tail current mirror, suppose we do have a DC voltage, common DC voltage at both the inputs. Again, if we vary this common DC voltage, then the voltage here it will vary, but then this current, since it is having very weak dependency on VDS through lambda, then hardly this current changes depending on the value of lambda, or you can say equivalent resistance. The variation here it will be very small. So, we may say that as long as this voltage it is such that transistor 3 it is in saturation region, then the quiescent current here it hardly depends on this common mode voltage, whatever we have said that this is V common, and if this input common mode voltage. So, if this current is not changing, then of course, DC voltage here and here they are also not changing. In fact, in case if we have common mode signal, then also you can say that the corresponding common mode signal coming at the two outputs, it hardly depends on the common mode input. In other words, if you see the common mode gain of say this circuit, which is, as we have discussed, minus Gm into R d divided by 1 plus 2 times Gm into R t. On the other hand, if you consider say this circuit, the common mode gain, it is minus Gm 1 into R d divided by 1 plus 2 times Gm 1 into R d s 3 or R O 3. Now, if you compare this part and this part, in fact, we can well approximate this by dropping this 1 and then the expression becomes R d divided by 2 times R O 3, whereas for this case the previous circuit this is becoming R d divided by 2 times R t, of course, with a minus sign. So, if you compare these two expressions, since R O 3 it is the output resistance of transistor 3 in saturation region, we know that R O 3 it is much higher than the passive resistor R t for equal tail current. I should say DC tail current, all right. And since this is much higher, then we can say that this the common mode gain of this circuit, having this active device at the tail, it is having much lower common mode gain. So, if I call say this is AC dash and this is AC. So, we can say that this AC dash it is much smaller than AC. So, that is why we say that it improves the common mode gain of the differential amplifier. So, now if you replace the load part by active current mirror, then what we will be getting is the improvement of common mode and differential mode gain. So, in fact, here we do have the small signal equivalent circuit, and using this small signal equivalent circuit, again you can derive the expression. And so, what we said is you already have compared. So, probably we can skip this part and we can directly go to the differential mode gain improvement by replacing the load part. Now, here we already have replaced the tail transistor, but then we do have the passive load. Now, these two passive loads, it can be replaced by active device as shown here. So, R d 1 it is getting replaced by transistor 7 and R d 2 it is getting replaced by transistor 8. And they are getting biased from this is of course a current mirror. So, we do have two transistor M6A and then M6B, both are diode connected and they are connected together, and suppose we do have some reference current. So, this is M6A, this is M6B, and then we are mirroring this current to say transistor 7. So, this is transistor 7 and then we do have some circuit connected here. Okay. Now, if I say that, let me call this is I reference dashed, and since by the virtue of current mirror, if I consider this transistor and this transistor, they are identical, then the current flow here, if I call this is I D 7, then I D 7 can be given as W by L of transistor 7 divided by W by L of transistor 6. Now, since these two transistors they are identical, we may say that W 6 is essentially summation of the two W's, W A plus W B. So, W 6 divided by L 6 is essentially summation of these two W's divided by the corresponding L, and L they are same, either we may say that L A or B, and so this is getting multiplied by I reference dash. Now, if I say all the transistors are identical, obviously this part it becomes 0.5 I ref, which means that only half of this reference current is flowing through transistor 7. So, likewise transistor 8 and M 6, it is forming current mirror. So, the current flow here it is again half of this I reference or I ref dashed. So, now we do have the reference circuit, which and it is having its reference current say I ref, and this reference current it is getting mirrored to transistor 3. So, if I call this is I D of transistor 3, which is equal to I reference multiplied by W by L of transistor 3 divided by W by L of transistor 4. Yeah. So, that's so we do obtain the current here in terms of I reference. Likewise, here also we can get the current relationship, namely I reference dashed, it becomes I reference multiplied by W by L of transistor 5 divided by W by L of transistor 4, by dropping 1 plus lambda VDS part. So, what we can say that this reference current, if say transistor 4 and 5 and 3 are identical, then we can say this is equal to I ref, this is also equal to I ref, and the current flowing through this transistor and this transistor, they are I reference by 2. So, this is also I reference by 2. And why? So, this 2 I reference, half of the 2 that I reference, together it is giving the total I reference here. So, that makes the current source coming from transistor 7 and 8, it is well balanced with the capability of transistor 3, which is working as current sink. Okay. So, let me summarize here what I like to say on this slide. If I assume that the this transistor and transistor 3 they are identical, then if I say this is I reference, that makes this current is I reference. and also this current is I reference. On the other hand, if I assume that all the 4 transistors they are identical, that makes this current equal to I reference by 2. Likewise, this also I reference by 2. So, that is how we can say that DC current wise. So, if and of course, this I reference current, it is in case if we have same DC voltage applied here, and if I consider M1 and M2 they are identical. So, that makes this I reference current, it is getting splitted into 2 parts, or equal parts are coming from 1 and 2, and that makes everything is getting well balanced. And in fact, this is very common, particularly for integrated circuit. We want to keep transistor 1, 2 anyway they should be matched, and likewise transistor 7 and 8 they should be matched. And in addition to that, whatever the bias circuit we do have or bias arrangement we do have. So, here also we want these 3 transistors in transistors they should be identical, and likewise not only these 2 PMOS transistor, but also the 2 bias transistors namely M6A and M6B, they should also be identical. And for integrated circuit, that is not very difficult to achieve, and that is frequently getting used. In fact, this arrangement as expected, since we are replacing the resistors here by active devices, the corresponding resistances offered by this active resistance or active devices, namely RO8 and RO7, they are much higher than the RD we do have here. And we know that the differential mode gain, it is equals to GM into RD, and since we are replacing this RD by these active devices, so we are expecting the gain should be higher. In fact, just for convenience, probably or to convince yourself, we can draw this small signal equivalent circuit here, and as you can see, the transistor 1 model of this transistor 1, it is given here. So, we do have RO1 and then GM1 into VGS1, VGS1 it is given here coming from primary input and whatever the source node voltage you do have. Likewise, we do have transistor 2, a model of transistor 2 here, which consists of RO2 and GM2 into VGS2, and VGS2 it is the gate to source voltage of transistor 2. So, this is the VGS2 that is coming from in 2 and whatever the source voltage you do have, and then transistor 7 and transistor 8 they are giving RO7 and RO8. And then if you analyze this circuit, what we can find that the common mode gain, to get the common mode gain, we have to make V in 1 equals to V in 2 equals to V in common, and in that case both the voltage here and here they are same, and left half and right half, assuming these 2 resistors are identical, the left and right half are identical. So, probably we can split this resistor into 2 equal parts, as we have discussed before, namely 2 times R O 3 here and 2 times R O 3 here, and then we can remove this part. And then this voltage, of course, this is V in C, this is also V in C, and then from that you can find the both V O 1 equals to V O 2 equals to V in C multiplied by G M 1 or 2, then multiplied by R O 7 or 8 divided by 1 plus this degenerator. So, that is G M 1 2 multiplied by 2 times R O 3. And so, this is the both the outputs are same. So, we can say that this is the common output voltage for common mode operation. And we can so likewise, so you can get the corresponding common mode gain. It is, of course, it is having a minus sign. So, that gives us common mode gain equals to G M 1 R O 7 divided by 1 plus G M 1 2 times R O 3, right. So, for differential mode of operation, so by replacing these two transistors, what we are getting is the common mode gain, of course, it got increased compared to the original circuit, but the differential mode gain, it is also getting increased. So, this increase of the common mode gain, it may not be having any drastic effect, as the differential mode gain is also getting increased. Now, for differential mode gain, what you can do in this circuit for differential mode gain, we can make V in 1 equals to V in D by 2 and V in 2 equals to V in D by 2 with a minus sign. And we do have all these elements R O 7, R O 8, then this is G M into V G S 1, G M into V G S 2, and so this is V in D by 2 with a plus sign, and this is equal to minus V in D by 2. And as we have said earlier, that makes this node virtual ground. So, we can simply then split this part, and then we can find the expression of V O 2 equals to. So, since this is AC ground, so this is equal to G M into R O 7 in parallel with R O 1 multiplied by the differential, half of the differential input, and with a minus sign. So, likewise, if you consider V O 1, so that is equal to minus G M, of course, this is 1 and this is 2. So, we may drop that subscript 1 or 2, assuming they are equal. So, this is multiplied by R O 8 in parallel with R O 2 multiplied by V in D by 2 with a minus sign here. So, this minus and this minus, they are getting cancelled. So, we can remove that. So, from that we can see the differential output V O D equals to V O 1 minus V O 2. So, that is equal to G M into R O 7 in parallel with R O 1, assuming the respective terms are equal. So, this multiplied by V in D, and from that we can get, from this you can get the differential mode gain equals to G m into R O 7 in parallel with R O 1. So, now the differential mode gain got increased from the previous value. In the original circuit it was AD, it was GM into RD. Though these two resistors they are coming in parallel, but you may recall this RD, it was in parallel with RO1, and definitely this is much higher than this one. As a result, this new AD, if I call this is AD dashed, it is much higher than previous AD. So, we can see that is how the circuit gain it is getting changed by deploying the current mirror in differential amplifier. So, we have discussed about the MOSFET differential amplifier. The situation it is very similar if you consider BJT version. Let me take a break and then again we will be coming back.